Welcome to the wonderful world of analysis. In this video we're going to explore a few of the theorems from the end of chapter 2, and one thing we're going to get to do once we have these theorems is we're going to get to prove honestly that the reals are an uncountable set. Now this is a fact that we've used, that we've relied on in class, but we haven't, strictly speaking, yet proved it. To prove it we need to use the following theorem. The theorem states if I have a sequence of nested closed intervals, so I sub n is going to be a closed interval of the form a sub n to b sub n, and the nesting means I1 contains I2, and I2 contains I3, and so on. Okay, so what we can prove once we have this set up is that the countable intersection from n equals 1 to infinity of I sub n is non-empty. Okay, so let's set about proving this. So what I have here is, from this nesting assumption, I sub n, which is a sub n to b sub n, this contains the next one, I sub n plus 1, which is a sub n plus 1 to b sub n plus 1. What I get is I can now sort of start stringing these things together, and I can see that, in particular, a sub n has to be less than or equal to a sub n plus 1, which is less than or equal to b sub n plus 1, and because I sub n contains I sub n plus 1, this has to be less than or equal to b sub n. Okay, so this is not, strictly speaking, yet part of the proof, but this is a useful fact to have. So what I can do now is I'm going to define a set E of just, let's say, the left endpoints of my intervals. So a sub n equals 1 to infinity. Okay, E is a non-empty set. In particular, I know A1 is in E. I know A2 is in E. There are lots of elements in there. They may not be distinct, but I certainly know there's something in there. It's non-empty, and in particular, E is bounded above. Okay, well, how do I know E is bounded above? In particular, I can say for all x in E, right, x is less than or equal to B1, the right endpoint of the first interval. Well, why is this true? Well, I know if x is in the set E, x equals a sub m for some integer m. Okay, so some integer m, that means a sub m, I know, is less than or equal to b sub m, and by the nesting assumption, I know that b sub m is going to be less than or equal to b sub m minus 1, which is less than or equal to b sub m minus 2, and I can start stringing these together. By the nesting assumption, I can eventually get as less than or equal to b1. So I have an upper bound. Okay. Now, in particular, what I wanted to do with this upper bound is I have an upper bound of a non-empty set. The reals have the least upper bound property, so that tells me, in particular, the supremum, which let's call alpha, exists in R. Okay, so I have a supremum, and now I have something to work with. The claim I'm going to make is that alpha, this supremum, is in fact in the set E. Of course, the supremum doesn't always have to be in the set E, but in this case, we're going to prove that it is. Okay, so again, by our nesting assumption, we have the following string of inequalities. I know A1 has to be less than or equal to A2, less than or equal to A3, and so on. I can go up to, let's say, AK, which has to be less than or equal to B sub K, which B sub K is less than or equal to B sub K minus 1, and so on. Okay, and this is true for all natural numbers K. Okay, so let's assume if our supremum alpha, let's say this is greater than b sub m for some m. Okay, and what we're going to do is we're going to show we have to get a contradiction from this. Now, if this is true, this means b sub m, right, this is less than, strictly less than, the supremum of these a sub n's, about how we've defined it. That means, since it's smaller than the supremum, there exists a natural number, we can call it L in the natural numbers, so that b sub m has to be strictly less than a sub L, which is less than or equal to our supremum alpha. Now this is clearly a contradiction. This contradicts this string of inequalities which we have written up here. Okay, all the a's have to be less than or equal to every single b. So that definitely cannot happen. What we can now conclude is that x is less than or equal to, let's edit this part out too, to here, please. So alpha is less than or equal to b sub m for all m in the natural numbers. Okay, so what we have then is, since it's a supremum, we have this nice inequality. It has to be greater than or equal to a sub m, and it's less than or equal to b sub m. So this tells us that alpha is in this interval I sub m. And this is true for all m in the natural numbers. So we're definitely going to have this in the intersection. So alpha is in the infinite intersection, n equals 1 to infinity, I sub m. Okay, so that in particular shows us this intersection is non-empty. The supremum is inside it, the supremum of the left endpoints. Now there could be more things in there, but once we have one, we've shown enough to be non-empty. Okay, and now that we have this, we can actually prove a nice, provide a nice proof that the real numbers are uncountable. And rather than do this directly like we might by doing binary expansions, we're going to do this indirectly. Let's assume not. Okay, then we know it's an infinite set, since in particular it contains the natural numbers, which is an infinite set. If it's not, it has to be countable. So then there exists a function f from the natural numbers to the reals that is a bijection. Okay, so it would have to be a countable set. It is equivalent to the reals. So basically we can enumerate the real numbers by x1 is f of 1, and x2 is f of 2, x3 is f of 3, and so on. Okay, so then if this is true, our real numbers, they've been enumerated, we can list them. It's going to be the set x1, x2, x3, and so on. Okay, so what I'm going to do is I'm going to now take I1, which is going to be a subset of R. Let's let this be a closed interval that doesn't contain with x1 not in I1. So basically, if I think of my real numbers, I have this x1 here, I could do something over here, or I could have I1 over here. Okay, it really doesn't matter, I just need to pick one side. Okay, so what I'm going to do next is I'm going to then take my I1 and I'm going to let I2 be a subset of I1, again be another closed interval, with x2 not in I2. Okay, so I've just defined it so that I2 is a closed interval contained in I1 that doesn't contain x2. Okay, and then I'm just going to go ahead and I'm going to define a sequence here inductively. Define I sub n inductively is going to be the way to do it. This is going to allow me to define infinitely many things in one step. Okay, we're going to define it inductively by, we're going to take I sub n. Let's see, I sub n is going to be a subset of I sub n minus 1 with, I'm just going to throw away one point, make sure x sub n is not in I sub n. Okay, so sort of in pictures here, I have my I sub, let's say n is right here. Let's say x sub n is outside of it. That's all we needed. If, say, x sub n plus 1 is here, I'm just going to choose my I sub n plus 1, something that doesn't contain that. Okay, and I can keep doing this forever, and they're nested. So then I sub n is a nested set. Okay, a nested set of closed intervals. So that means, by the last theorem that we proved, their infinite intersection is non-empty. All right, so I is going to be the infinite intersection, and again, it's a countable intersection by the assumption that my reals were countable. So I've just created a countable collection of these subsets. Okay, so I is my countable intersection of these. It's non-empty, but what I've done is I've constructed this so that xj is not in this interval, in this set I, for every natural number j. Okay, and this is true since xj is not in ij by definition, so it can't be in all of them. So this tells us there exists a real number x that is not in this enumerated set x1, x2, up to, well, I guess it doesn't end because it's uncountable, or countable. This is our contradiction. So therefore, our assumption that the reals were countable is flawed. The real numbers are uncountable. Okay. And once we have that, we can prove a very nice corollary. The irrational numbers are uncountable. And the proof of this is actually very simple, very straightforward. Let's just assume, let's assume none. Okay, so let's assume our irrational numbers, let's call it I, r minus q, is countable. Okay, then, by, in fact, Theorem 212, what we're going to get is I union q is the union, a finite, so hence definitely a countable union, of two countable sets, is countable. Well, I is r minus q, so I union q is r. So this tells us r is countable, which we just showed is false. This is our contradiction, therefore the irrational numbers are uncountable. And that's what we wanted to show. Now what we can next do is we can show that this is called the Heine-Borel theorem, which says if I have a set in Rk, and we're just going to focus on the case when k is equal to 1, with our standard metric is compact if and only if E is closed and bounded. Okay. Now what I would note here is this is a special case. This is not the definition of compact. Okay, if I change the underlying set or I change the metric, this can be made false very quickly, very easily. This equivalence is very special only for the real numbers and copies of the real numbers Rk. Now in fact, we're not actually going to prove this, but what one can prove instead is the following theorem, which is very nicely laid out in the book. It says if E is a subset of Rk, the following are equivalent. E is closed and bounded, E is compact, and every infinite subset of E has a limit point of E. Now the proof in the book is quite nice, so I'm not going to actually go through the proof here. What I'm going to say here is what we have is three statements. I have statement A, I have statement B, and I have statement C. The following equivalent says A implies B, but also B implies A, and B implies C, C implies B, A implies C, and C implies A. Now, to prove this, if we tried to prove if and only if at every step, we would end up proving 6 implications. Now that's just too much to do, and in fact we can be much more clever and do half the work. So if we start with these statements, if I show A implies B, and then B implies C, if I can show C implies A, I actually have the equivalence. Because A implies B is clear, but B is going to imply A by way of C. So B implies C, which implies A, so B implies A. We get that for free. B implies C is clear, but C implies B because C implies A, which implies B. So we're basically able to cut down half our work. Now, the proof in the book is very nicely done, so I'm going to say that would be a good thing to read through.